All right, let's get right into it. Magnetic resonance imaging, MRI, is easily one of the most powerful tools in all of modern medicine. But how does it actually work? Today, we're going to pull back the curtain and break down this incredible technology step by step, all the way from the patient to that final, detailed picture.
So you've probably seen one of these things. It looks kind of like a giant donut from the future. And the question it brings up is fascinating. How does this massive machine see inside the soft tissues of your body with such mind-blowing detail, all without using a single bit of harmful radiation like an X-ray or a CT scan? Well, the answer is this beautiful dance of physics, and it all starts with you.
So, to figure this out, we're going to walk through 5 key stages. We'll start with the raw ingredients that are already inside your body. Then, we'll see how we can get those ingredients to create a signal. After that, we have to figure out how the machine knows where the signal is coming from. That'll lead us to this strange blueprint called K-space. And finally, we'll see how that blueprint gets turned into the detailed picture a doctor can actually use.
First things first, let's talk about the fundamental building blocks. You see, the only reason MRI is even possible is because our bodies are, in a very real way, naturally magnetic.
And it really all boils down to water. Our bodies are mostly water, H2O. And that H, hydrogen, that's the real star of the show here. Every single hydrogen atom has a single proton, and that proton behaves like a tiny, tiny spinning magnet. This is the raw material we're going to work with.
And this image right here shows a pretty dramatic transformation. On the left, that's what's happening inside you right now. All those trillions of tiny proton magnets, they're all just spinning in totally random directions like a chaotic swarm of bees. They completely cancel each other out. But on the right, when you slide into that super powerful magnetic field of the MRI scanner, something incredible happens. A tiny fraction of them suddenly snap into alignment with that main field. They stop being a chaotic swarm and become more like an organized army, all pointing in roughly the same direction. And that creates a net magnetization that we can finally measure.
Okay, so we've got our protons all lined up, but just having them sit there doesn't really do much for us. The next big step is to get them to talk to us, to generate a signal that the machine's antennas can actually pick up. And this is where the resonance part of MRI comes into play.
Now, resonance is a really cool concept in physics. Think about pushing someone on a swing, right? If you just push randomly, nothing much happens. But if you push at just the right rhythm, the resonant frequency, you transfer energy super efficiently and they go way higher. It's the exact same idea in MRI. We send in a radio wave pulse at the perfect frequency for those hydrogen protons.
So what does that radio frequency pulse actually do? Well, it injects a quick burst of energy that literally knocks that net magnetization, that's M here, sideways out of its alignment with the main magnetic field, B0. It's kind of like tipping over a spinning top. For just a split second, the protons have absorbed that energy and they're in a new, higher energy state.
But that energized state is temporary. The protons naturally want to relax back to where they were, realigning with that big magnet. And as they do that, they have to release the energy they just absorbed. They do it by sending out a very faint radio signal. You can think of it like an echo. And the MRI machine is basically a giant, super sensitive antenna, listening for these tiny little echoes. Now, here's the crucial part. Protons in different tissues, like fat versus water, relax at different speeds. And that difference is what creates the beautiful contrast we see in the final image.
So we can make a signal and we can hear it. Awesome. But that signal is coming from trillions of protons all over the body, all at the same time. This leads us to the biggest challenge in any kind of medical imaging. How do you know where each piece of the signal actually came from?
I mean, really think about it. It's like being in a huge stadium and everyone is shouting at once. How on earth could you pinpoint where just one specific voice is coming from? The MRI machine faces that exact same problem, but it has a really, really clever solution for giving every single point in your body a unique address.
And the answer is a set of smaller, weaker magnets called gradients. They do their job in a 3-step dance. First, a slice selection gradient turns on. This makes it so only a thin slice of your body, say through your head, is at the right magnetic strength to get excited by the radio pulse. So we've isolated a 2D plane. Next, a phase encoding gradient gives a quick pulse. This makes the protons get a little out of sync, or out of phase with each other, based on how high or low they are on that slice. And finally, a frequency encoding gradient turns on while we're listening for the signal, which makes the protons spin at slightly different frequencies based on how far left or right they are.
And just like that, boom, we have our address system. Every single spot within that 2D slice now has a totally unique combination of phase and frequency. It's just like having a grid reference on a map. The machine can now tell the signal coming from the tip of your nose from the signal coming from your left ear because they have completely different magnetic addresses.
Okay, this is where things get a little weird, a little more abstract. But you have to stick with me because this is the absolute heart of how an MRI image is born. All of this address information, all this data about frequencies and phases, it's not an image yet, not even close. It has to be stored somewhere first. And that data storage space has a special name, K-space.
So let me be super clear about this because it's the #1 misconception. K-space is not a picture of your brain. If you looked at it, you wouldn't recognize a single thing. Instead, it's a grid, a matrix, that maps out all the different frequencies that make up the final image. Think of it like a musical score. The written score isn't the music itself, right? But it contains all the information an orchestra needs to play the symphony. K-space is the score for our image.
There's this quote from one of the classic papers on MRI that just captures this idea so perfectly. It says, "The process is like running trails through a K-space, and the signal you measure is just the value of the landscape at each point you visit. The gradients we just talked about, they're basically the steering wheel, letting the scanner fly a specific path through this K-space and chart the whole terrain." And this right here is what that K-space landscape actually looks like. That super bright spot in the center, that's where all the low-frequency data is stored. This is the most critical data. It contains all the basic contrast and the overall shape of the image, the big picture stuff. Then, those dimmer areas out toward the edges, that's where the high-frequency data lives. This is all the fine detail, the sharp edges, the little textures. You absolutely need both to build a complete, high-quality picture.
And it turns out there isn't just one way to fill in this data map. Different types of scans use different flight paths or trajectories to chart out K-space. The most basic is a Cartesian scan, which fills it in line by line, kind of like an old dot matrix printer. A radial scan collects data like the spokes on a wheel, radiating out from the center. And a spiral scan, you guessed it, charts the landscape in one continuous spiral. Each path has different pros and cons when it comes to speed and image quality.
So, how does this all come together in the end? We've done all the hard work. We've collected the raw data. We've meticulously charted that weird K-space landscape. Now it's time to turn that abstract blueprint into a real picture.
And this really is the final leap, isn't it? We have this grid filled with complex numbers that represent all these different waves. How in the world does a computer translate that into the amazingly detailed pictures of our anatomy that we're all used to seeing? Well, the answer lies in one of the most powerful tools in all of mathematics.
The magic decoder ring is something called the Fourier transform. Now, you don't need to know the complex math behind it, you just need to know what it does. It's a process that can take a super complex signal made up of tons of different frequencies, like our K-space data, and it can instantly break it all down, mapping every single piece back to its original location in space. It basically translates the language of frequency into the language of pictures.
And this progression here just brings the whole thing to life. Look at the image on the far left. That's an SNR, a signal-to-noise ratio of 1. That's what you get when you've barely filled in any of K-space. It's almost pure static. But as we move to the right, the scanner is filling in more and more of that K-space map, collecting more data. You can literally watch the image emerge from the noise, getting clearer and sharper until it's crystal clear at an SNR of 50. So that's really the ultimate takeaway here. The quality of an MRI is directly tied to how well and how completely the scanner can chart that K-space landscape. A more complete map with a strong signal and very little noise gives you a beautiful, sharp image that a doctor can use to make a diagnosis. A rushed or incomplete map, that gives you a noisy, blurry mess.
And that brings us to one last thought, a question that really points to the future of MRI. If scanning is really just about flying a path through K-space to chart it, what if we could make that path smarter? Researchers right now are using AI and neural networks to try and learn the absolute perfect, most efficient path for every single scan, custom tailored to exactly what they're looking at. What kind of new possibilities could that unlock for speed, for resolution, and for our ability to see inside the human body? It's a pretty exciting time to be charting this landscape.